Hi everybody! We're going to be starting our next chapter on exponents and logarithms. And I know you've never heard of logarithms before, but let's just say you need to know your exponents in order to work with logarithms effectively. So over your summer, you did a little bit of work on exponents. And so most of this should be pretty familiar to you. First off, let's talk about exponents and the product property. Okay, basically when you're multiplying two bases that are the same, you can add their exponents. So we have 3 to the 4th times 3 to the 5th. What we'll just do is add the 4 and 5 and we get 3 to the 9th. If you wanted to do that on your calculators, you could, and you would get 19,683. But honestly, what I'm really concerned with is that you know that that's 3 to the 9th. Okay? When we're dealing with power of a power, we're going to multiply those exponents. So our example here, 3 to the 4th to the 5th, we will multiply the 4 and the 5, and we will get 3 to the 20th. We'll leave it at that. Power of a quotient. Basically, if you have a fraction that is being raised to an exponent, you should raise both the numerator and denominator to that exponent. So for our example here, we would get 2 to the 4th divided by 3 to the 4th. Now, in your summer packet, we told you to memorize some of these values. So you should know right off the bat, 2 to the 4th is 16, 3 to the 4th is 81. If you do not know those values, it's time to start memorizing. Okay, power of a product. Kind of the same idea. We have to apply this exponent to everything inside these parentheses. Notice this is just one term in here. So all we get is one term on the outside, x to the 4th, y to the 4th. And our quotient property, when we are dividing and we have the same base, we subtract our exponents. So 3 to the 8th divided by 3 squared, we basically do 8 minus 2, and we get 6. Okay? And you might know that that is 729. Okay, so let's move on a little bit. That should have all been old news. So now what we want to do is we want to talk about taking some values and simplifying them. And again, this goes back to what you did last year in Algebra 2, but it also goes back to some of the memorization you did this summer. I do want to remind you that when we have something raised to a fractional exponent or a rational exponent, we can rewrite that as a radical. I want you to remember that whatever the denominator is here, that is the index of our radical. Okay, and whatever the numerator is here in our power, that would actually be the exponent in here. It's just 1, so we didn't write it. So I'm going to work through a couple of problems with you, and hopefully you'll remember these. Hopefully it'll spark some things in your mind. So when we look at the first one, it says evaluate 625 to the 1/4. First of all, 625 should jump out as, oh, that's a number I remember. That is 5 to the 4th power. So I've just renamed 625 as 5 to the 4th. And that is being raised to the 1/4 power. Now, this is where we have to go back and we have to think, power of a power, we multiply. So, 4 times 1/4 is 1. In fact, you might even think of it like this, where these would cancel each other out. Which means this simplifies down to 5. Okay, so think about that. Let's move on to the next one. We have 3 to the 1/2 times 21 to the 1/2. So I would probably turn these into the square root of 3 times the square root of 21, which is the square root of 63. Now, what is the largest perfect square that goes into 63? Well, it's 9. So we can do a little rewrite here. That square root of 63 is root 9 times root 7. And of course, we know that the square root of 9 is 3. So So we get 3 root 7 as our answer. Square root of 7 cannot be simplified. You might see it written as 3 times 7 to the 1/2. That would be the same answer. So I want you to stop the video and go ahead and try number 3, which is very similar to number 2, but you're dealing with third powers. And let's see how you can do. So stop that video and try that problem. Okay, so take a look and let's see how you did. Okay, we turned these into cubed roots, and then because they were both cubed roots, we were able to multiply them and make it a cubed root of 120. And then, of course, we have to think about our cubes list, not our perfect square list, and break that down. Okay? So let's take a look at the next few problems, and let's see what we can do. So the first one, number 1, we have 27a to the 6 raised to the 1/3 power. So first of all, 27 should be a familiar number. 27 is 3 to the 3rd. And then, of course, we have a to the 6th. And all of that is being raised to the 1/3 power. Now, our power to a power property says that we multiply, and our product, the property that we had right here, power of a product, tells us that we essentially have to apply the exponent to each element inside that monomial. So we would actually have 3 to the 3rd to the 1/3, and a to the 6th to the 1/3. To be honest, I wouldn't normally write this out, but I'm going to write it out right now, just so you can take a look at it. And when you look at that, what I hope you'll notice is that, first of all, 3 times 1/3, those 3's cancel each other out, so we're just left with a plain old 3. And when we have 6 times 1/3, these can simplify, and so we're left with a squared. Okay, so that's our answer. We've just simplified that. The next one is written a little bit differently, but it essentially works out to be the same kind of problem. So we have 8x to the 12th, and we're taking the 6th root of that. First of all, 8, you should know, 8 is 2 to the 3rd, and x to the 12th. Okay, so I haven't really changed too much. But instead of taking the 6th root, I'm going to raise that to the 1/6 power. And again, all we're doing is interchanging between a root and a rational exponent. The reason I did that is now I can think of this as 2 to the 3rd to the 1/6, and we multiply power to a power, and x to the 12th to the 1/6, which would also be multiplying because it's power to a power. So let's take a look at what we have. 3 times 1/6, these reduce, and we wind up with 2 to the 1/2. 12 times 1/6, these reduce, and we wind up with a 2 in our numerator there of our exponent. So we wind up with, extend my page, 2 to the 1/2 times x squared. Okay, now typically because we've been given this problem as a radical, we give our answer back as a radical. So we have to put this as the square root of 2, and we can take our x squared and put that out in front. So we get x squared root 2. Okay, so the next one, again, very similar idea, but you might be looking at 192 and thinking, oh, I don't remember that one. Well, you don't remember that one because it's not one of the numbers that jumps out at us. It's not a cube, okay? So what we have to do is we have to think about our list of cubes, and we have to think about what would be the largest of these numbers that would divide into 192 evenly. Well, 125 doesn't go in. And if you checked on your calculator, you would see that 64 does go in. Let's do a little rewrite and have the cubed root of 64 times 3, and then x to the 5th, y to the 7th. Now what we can do is we can say, well, what is the cubed root of 64? It's 4. And we're going to be left with the cubed root of 3 inside. See, that could be simplified right there. X to the 5th, we can take some of the x's out, but some have to stay in. So the way that I do it is I say 3 goes into 5 one time, and we have 2 left over. So the leftovers stay under the radical. Okay, let's do that again, and now let's do it for y to the 7th. 3 goes into 7, I put a y here, 2 times, with a remainder of 1, so y to the 1st inside. And that is our answer. I'm not sure how your teachers taught you it last year. They may have said, oh, do a rewrite like this, where you have 64 times 3, and you might have broken that x to the 5th down to be something like this. And you might have broken the y to the 7th down to look something like this. You know, that also works. It's a very similar idea. You're looking at what can you take out. Well, I can take this out, I can take this out, and I can take this out. This way is going to be definitely more efficient for you. Okay, so I'm always going to try to teach you how to be more efficient. Okay, so what I'd like for you to do is I'd like for you to see if you can do the next few problems. Okay, try 1, 2, and 3 here. Think about those numbers, the list of numbers that you've studied. See what you can do. Okay, so pause the video, and then come back and see. I'll work through some problems with you. Okay, so let's take a look at number 1. Okay, so number 1, I think it would be best to rewrite this as I have it here. And then what you can see is that these 5s will cancel each other out. You're left with 3 to the 4th, and 3 to the 4th you should know is 81. 3 times 3 times 3 times 3. The second problem, there were actually 2 ways that I thought you might do this one. So I'm showing you the first one right here, and that is to take the 27 and rewrite it as 3 cubed. When we do that in the numerator, what we get is these 3's will cancel each other out. And again, that's because we have 3 times 5/3 in our exponents. Okay? And the same thing happens here. Okay, so what we wind up with is 3 to the 5th divided by 3 squared. 3 to the 5th divided by 3 squared, you would subtract your exponents, and we would wind up with 3 cubed. And again, you should know that that is 27. Now, maybe you didn't see that way. There's actually another way to do this. You see, we have the same base of 27 here. Because we're dividing, we can subtract our exponents. So you may have thought of this as 27 raised to the 5/3 minus 2/3 power. Well, 5/3 minus 2/3, we keep our base. We wind up with 3/3. And what is 3/3? Well, it's just 1. So again, we would get 27 for that answer. I don't have a preference to either of these methods. It's kind of what jumps out to you. Okay? Number three, I did a little rewrite. And what I noticed is the first 16 was being raised to the 3/4 power. So I wanted to express it using something to the 4th power. And the second 16 was being raised to the 1/2 power, so I wrote it as 4 squared. The whole reason I did that, cancel, cancel. And over here, cancel, cancel because of the multiplying. So what I'm left with here is 2 cubed. Well, 2 cubed is 8. And here I'm left with 4 to the 1st power, which is just 4. 8 times 4 is 32. Okay? So listen, that gives you a pretty good foundation. I believe you should be able to try the next few problems. Okay, stop the video. As I said before, stop the video. Try those few problems, and then I'll give you some solutions in a little while. Okay, so go ahead and do that. Okay, here are the solutions. Okay, again, these are numbers that you should know, 32, 125, and 196. Notice I put the 2 in this little index. Normally I won't do that for square root. And then these are just like the problems we just did. 5 goes into 15 3 times. 5 goes into 10 twice. Cubed root of 125 is 5. 3 goes into 18 6 times. And this was just a square root right here. Okay. Next 3 problems, what I'm going to tell you that you need to do is you need to get common denominators. So I'm going to do this first one. I'm going to leave you to do 3 and 4. We're asking you to write these as a single radical. So what we're going to do is we're just going to kind of leave the 5 out here. And I'm going to look at x to the 3/4 and y to the 1/2. The least common denominator for those exponents is 4, which means I'm going to have to multiply this exponent by 2 over 2. As a little rewrite, what I get is x to the 3/4, y to the 2/4. Why did I do that? Well, the direction said that I have to express this using a single radical. So what I'm able to do now is keep my 5 out there and rewrite x to the 3/4 as the 4th root of x cubed and y to the 2/4 as the 4th root of y squared. And now I have it expressed as a single radical. So stop this video, go ahead and do 2 and 3, and then start the video up and see if we agree. Okay, check your answers. Let's see how you did. Least common denominator here, 5 and 4 would be 20. So I multiplied the x, I didn't write it out, but I multiplied it by 4 over 4, and I multiplied the y by 5 over 5. Okay, so check 2 and 3. And then we're going to take a look at these equations at the bottom of the page. So if you look at the equations here, we're going to solve these as we would any other equation. The first thing we're going to do is PEMDAS backwards. We're going to get that exponent, or that variable alone. We're going to add 9 to each side. When I add 9 to each side, I get 625 equals x to the 4/5. Now you should be thinking 625 is familiar. 625 is 5 to the 4th. And then we have x to the 4/5. How do we get rid of that rational exponent? Well, what we can do is we can raise each side to the reciprocal power. In other words, let's raise this side to the 5/4 power. And as long as we do the same thing to the other side, our equation will be balanced. It's just, we have one term on the left and one term on the right, so we're able to do that. What happens on the right side, you'll notice 4 over 4 cancels, 5 over 5 cancels, and we are left with x. On the left side, the 4 over 4 happens to cancel, and we're left with 5 to the 5th power. I believe that was on your packet. 5 times 5 times 5 times 5 times 5 is 3,125. So think about what we just did. Think about isolating the x value and then raising it to the reciprocal power. And go ahead and see if you can do 2 and 3. Okay, so hopefully you were able to get this far. What this does on this problem, the 4 and the 4 cancel out, the 3 and the 3 cancel out, and we're left with x. On the left side of the equation, 4 over 4 cancels out. We're left with 3 to the third. Well, 3 to the third is 27. You know that one. On number 3, hopefully you were able to simplify it to this step. And again, the right side, these cancel out, and we're left with x. On the left side, the 3 over 3 cancels out. We're left with 6 squared, which is 36. Whew, that was a lot. Okay, go back through. See if you remember. See if you have any questions. Please star anything that you have a question on. And we're going to do some more work with this together. Have a great day, everyone.